Imagine a digital mind capable of exploring realities that do not yet exist, one that can simulate entirely new forms of life, not in our classical world, but in the strange, rule-defying realm of quantum mechanics. This is not science fiction. At the intersection of artificial intelligence and quantum simulation lies a radical frontier, training AI to imagine and test hypothetical quantum organisms, life forms that could exist, not on Earth, but in exotic quantum environments governed by superposition, entanglement, and non-locality. At first glance, this may sound like speculation, but just as mental rehearsal activates real brain circuits to prepare us for action, AI-driven quantum simulations activate real quantum-instructed models to explore what kinds of life might emerge under unfamiliar rules. These are not biological organisms, but mathematically and physically consistent systems that mimic lifelike behavior, adaptation, reproduction, or decision-making, using quantum properties rather than classical mechanisms. In this way, AI becomes the imagination engine of quantum science, visualizing what evolution might look like if it unfolded in a universe where particles exist in multiple states at once, or influence each other across vast distances. How can AI simulate such non-intuitive systems? The answer lies in reinforcement learning and quantum-inspired neural networks, which allow artificial agents to explore possible environments defined by quantum rules. Just as neurons wire together through repeated activation, AI models evolve their own internal representations, quantum policies, through repeated interaction with quantum mechanical scenarios. Here, fitness is redefined, not survival in a harsh landscape, but coherence preservation, entanglement utilization, or energy efficiency in decoherence-prone environments. Consider the analogy of an AI trying to evolve a quantum walker, an entity that navigates a complex lattice not by choosing one path, but by interfering with all possible paths simultaneously. Through quantum simulation, the AI adjusts parameters like entanglement depth, decoherence resistance, and interaction strength, essentially mutating quantum traits to discover which behaviors are stable, adaptive, or even lifelike. Over time, the system begins to exhibit surprising patterns, oscillations that resemble breathing, feedback loops that mimic metabolism, and non-classical memory that recalls past states probabilistically rather than deterministically. Which computational architectures make this possible? Evolving quantum simulations rely on variational quantum circuits, tensor networks, and hybrid quantum classical models. These architectures are flexible enough to encode a range of quantum states and interactions, yet scalable with AI training techniques like backpropagation and gradient descent. Quantum simulators, both digital and analog, provide a sandbox where AI can probe quantum possibilities, test emergent behaviors, and fine-tune parameters that might never be accessible in a physical lab. And what of real-world implications? Just as visualization in athletes and musicians primes neural circuits for success, evolving AI in quantum simulations primes scientific discovery for future technologies. Simulated quantum organisms could inspire new classes of quantum sensors, robust quantum error-correcting codes, or even artificial quantum life with applications in computing and communications. In the same way that deep learning first succeeded by mimicking human perception, AI might now surpass classical intuition by simulating the unimaginable. Quantum evolution, unconstrained by biology. The effectiveness of these simulations depends on fidelity, interpretability, and creative constraints. Too much freedom, and the AI generates noise. Too little, and it merely reproduces known phenomena. The most promising results arise when AI is guided by physical laws, yet allowed to explore beyond human expectation, with feedback loops from real quantum hardware, cross-section against experimental results, and multi-agent interactions. The AI becomes not just a simulator, but a hypothetical biologist, asking what forms of life are possible if the rules of the game are changed. Looking ahead, quantum-enhanced AI will benefit from platforms like quantum cloud computing, neuromorphic processors, and AI-accelerated quantum design environments. These technologies will enable deeper, more intuitive explorations of emergent quantum behavior. Just as VR enhanced visualization by engaging multisensory circuits, these new tools will immerse AI in quantum logic spaces where hypothetical organisms can be tested, evolved, and even interviewed about their simulated experiences. Ultimately, using AI to simulate quantum organisms redefines the boundaries of life, intelligence, and scientific imagination. By evolving digital entities that think, adapt, and exist in quantum terms, we begin to ask profound questions. Could life exist in quantum realms? What does it mean to be alive in a probabilistic universe? And most importantly, can artificial minds help us find answers beyond the reach of classical biology? The emerging evidence and the accelerating capabilities of AI suggest that they can. The idea of simulating quantum organisms using artificial intelligence combines the principles of quantum mechanics with machine learning to explore lifelike behaviors in non-classical environments. Unlike classical simulations, these systems evolve in Hilbert space, where quantum states are governed by superposition, entanglement, and probabilistic measurement, and AI enables efficient navigation of this exponentially complex space, searching for dynamic structures that resemble adaptation, replication, or memory. Researchers use variational quantum algorithms to simulate self-sustaining quantum states that maintain entanglement despite environmental noise. It's like training a flock of birds to perform synchronized flight in a room where gravity, air pressure, and even time fluctuate randomly. Quantum organisms are hypothetical constructs, coherent quantum systems designed to mimic biological traits like information retention, adaptive behavior, and interaction with an environment, and can be modeled as networks of qubits or bosonic fields with internal states that change based on entangled feedback loops. Their organism-like status stemming not from biological components, but from emergent properties driven by underlying quantum laws. A spin lattice network that reconfigures its structure to avoid decoherence pathways is treated as a primitive, self-adaptive entity. It's like sculpting a living maze that rearranges its walls to preserve an internal pattern even while being dissolved by rain. Machine learning algorithms, particularly reinforcement learning and neural quantum states, act as evolutionary engines that guide the emergence of complex patterns within quantum systems, adapting strategies based on feedback from the system's evolution and often discovering unexpected stability conditions or novel protocols, with AI learning not just optimal control pulses but also the structure of survival in quantum environments. A deep learning agent successfully learned to maintain high coherence in a superconducting qubit chain by dynamically modifying gate operations. It's like teaching a child to walk on a tightrope that randomly changes tension, angle, and length without ever falling. Quantum simulations can be designed as controlled ecosystems where virtual quantum organisms interact with each other and with the environment through entanglement, measurement, and decoherence, serving as digital laboratories in which AI agents apply selection pressures, introduce random mutations in system parameters, and observe resulting behaviors, with the complexity of interactions leading to emergent phenomena resembling competition, cooperation, or specialization. Simulated spin systems under AI-guided noise modulation have shown adaptive behavior resembling migration from unstable regions. It's like building a rainforest out of probabilities, then letting synthetic creatures figure out which branches are safest to rest on. When AI interacts with quantum systems over time, some configurations begin to exhibit persistence, adaptability, and optimization, features analogous to metabolism or cognition in biological organisms that emerge through trial and active learning and feedback optimization rather than explicit programming, with systems learning to minimize energy dissipation or maximize state fidelity without direct instruction. Quantum neural networks autonomously evolve to protect information in noisy environments, functioning like a primitive immune system. It's like a digital jellyfish learning to pulse only when the water is calm, adapting its rhythm to invisible ocean tides. By applying evolutionary algorithms within quantum simulations, researchers mimic a form of quantum Darwinism where AI selects for fitter states, those more stable, resilient, or efficient in their quantum behavior, using selection mechanisms such as coherence, duration, state fidelity, or functional complexity. and over successive generations, AI refines state configurations, much like natural selection favors advantageous traits. AI evolved a population of entangled states, where each offspring state preserved desired quantum correlations more effectively than its predecessors. It's like cultivating a garden of invisible flowers that only bloom under moonlight and letting the AI choose the ones that glow longest. The simulation of evolving quantum organisms faces formidable obstacles, including quantum decoherence, error propagation, limited hardware, and the exponential growth of state space. AI helps mitigate these challenges by compressing wave functions, predicting decoherence trajectories, and enabling real-time control, yet defining lifelike behavior in quantum terms remains both technically and philosophically. Hybrid quantum classical approaches using IBM Q systems demonstrated stable adaptive behavior for fewer than 10 qubits, but scaling remains elusive. It's like trying to raise a family of cats in a room where the furniture and the cats randomly teleport every few seconds. Recent experiments have begun validating AI-driven quantum control protocols, bridging theory and hardware in systems such as trapped ions, superconducting qubits, and photonic processors, revealing that even current quantum devices guided by AI can sustain and manipulate complex adaptive quantum states, while yielding theoretical insights into quantum cognition and synthetic agency that blur the line between simulation and realization. In 2023, researchers trained AI to stabilize entangled states for up to 100 times longer than passive protocols using active error correction strategies. It's like building a ghost orchestra where the conductor learns to anticipate every disturbance and still keep the music flowing. Simulating quantum organisms with evolving AI could revolutionize our understanding of life, intelligence, and complexity under quantum physics, potentially demonstrating emergent consciousness, quantum communication strategies, or new forms of synthetic cognition, thereby advancing quantum control and AI while challenging traditional definitions of life, agency, and information. Proposed next-generation simulations will use over 100 qubit systems with entangled AI agents to test for self-replication and adaptive quantum signaling. It's like building the first zoo of invisible creatures, each made of nothing but mathematics, memory, and possibility.